Hello, everyone. So this is the lecture on volcanoes and other igneous activity. So, we talked about igneous rocks. We talked about sort of the minerals that form them and different temperatures and pressures. And we briefly discussed in the last lecture about plutonic igneous systems, right? Dikes, sills, batholiths, laccoliths, magma chambers, things like that. But when those things are expressed at the surface, when they erupt, liquid magma on the surface, we get volcanoes. So my definition of a volcano really is any surface expression of the cooling of the earth. So that doesn't have to be just magma that erupts on the surface as lava. It can also be gases, any kind of volatiles coming out. Those are all expressions of the earth cooling. And generally, volcanoes are a vent in the Earth's crust from which molten or hot rock and gases issue forth. And on the surface, they look like a hill or a mountain composed of ejected material. So cooled ejected material that erupts onto the surface generally forms hills or mountains around the vent. And so that's a volcano. And so the major elements of the volcano are the mound of ejecta. So that's the stuff that's been erupted on the surface. And that could be either a mountain, in the case of, let's say, Mount St. Helens, a cone, which we see a lot in Iceland, or a dome. Here we have a cross-section of Hawaii, basically, kind of a generic hotspot island. And so it, in and of itself, is a mound of ejecta, if you look at these layers here. But then intruding into that is the source of the ejecta, or magma chamber. So the magma chamber is down here at the bottom, so the hot spot's moving up through the oceanic crust, and it's intruded into this volcanic island here. And these are successive layers of buildup. And then you also have this central vent, and that's kind of the source of the ejecta. So that's how the magmatic material gets from the magma chamber up to the surface. And if these were cooling, like here, this is a dike, right? And so a lot of dikes are central vents for volcanoes, but they're a dike when they haven't erupted yet. They're just down here. This would be a dike too, but at the top where it erupts, it's a volcano. So activity. So we have three names for the state of a volcano based on when it last erupted. An active volcano erupted in the last 10,000 years. So a volcano that erupted 9,000 years ago is still considered geologically active. Then a dormant volcano still has the potential to erupt, but it hasn't erupted in the last 10,000 years. But the magma chamber is still active. There's still vents. It takes a long time for stuff to reach the surface. And then we have extinct, so no longer a potential for eruption. So some of the volcanic islands that compose the northern part of the Hawaiian Islands, remember that plate has moved past the hot spot. There's no longer any active magma beneath those islands. Now the Big Island, for sure, there's active. I mean, it's erupting now, I think. But at the northern part, those are extinct. So no longer any potential for them to erupt. So what drives eruptions? Well, plate tectonics, as we've discussed, divergent boundaries have magma exposed at the surface, and subduction zones have magma exposed just up continent from the subduction zone. And then high temperatures and the melting of rock in Earth's interior. This is what we talked about in the igneous section. You get decompression melting, flux melting, things like that. That causes magma to move up through the crust and erupt onto the surface, whether that's continental crust or oceanic crust. So what triggers eruptions? Well, magma is under pressure, right? And as it's under pressure, it's being held in a semi-solid form in the mantle, and then as it decompress melts, the gases that are filled in that magma start to release pressure. And some triggers that could cause this is you could get a rock fall or a landslide, which releases the weight over the magma chamber, right? And so that releases some of the pressure, and then the magma can move up to the surface and erupt. You can get earthquakes, which basically precipitate a rock fall or landslide that causes that pressure to be relieved and the volcano to erupt. Or you can get the pressure in the magma just exceeds the strength of the overlying material. And this is as magma is moving into the magma chamber, and it hasn't erupted yet, eventually the pressure in that magma chamber is going to build up to the point where that magma is going to be forced upward. And then that facilitates decompression melting as it moves up. So in the example of Mount St. Helens, we had on March 20th, 1980, we had the intrusion of magma generating an earthquake. Then we had the continued intrusion of the magma that produced a bulge over here on the side. That bulge then subsided and caused a landslide, and that relieved the pressure in this upper part of the volcanic neck here, and then boom, we have a full-blown explosion. And down here, I want to give a shout out. This is, I'm trying to remember his name. It's not a good shout out. This is the geologist that was observing the volcano at the time it erupted, and he passed away from it. So this is what Mount St. Helens looked like pre-eruption, you know, nice snow-capped, almost textbook volcanic mountain here. Beautiful forest, Spirit Lake down here. And then after the eruption, taken from almost the same angle, the bulge subsided into this landslide here. This erupted, forming a kind of half a caldera here. Spirit Lake got filled in with debris, and all of the vegetation got blown away. So pretty powerful eruption. So what drives eruptions? Mostly gas pressure in the magma. So down here at about 2 to 3 kilometers below that, right, the gas is dissolved in solution, but it's not water vapor yet, it's not carbon dioxide yet, it's not O2 yet, it's just single atoms of carbon, single atoms of oxygen, single atoms of, say, sulfur, whatever, just in the mix, but they're under so much pressure that they can't leave the mixture. They can't form bubbles. There's too much pressure on this magma chamber. At about 2 to 3 kilometers, you get bubbles starting to nucleate or form. The bubbles expand as that magma moves up and continue to nucleate into larger and larger bubbles. But those bubbles are surrounded by magma, so those bubbles are very much still in solution, but they're just starting to form as the pressure is released. Then when you get to about 100 to 300 meters, the bubbles then become about 75% of the magma by volume. And that's about where you get to the base of the fountain here, right? This is when the pressure of the gas is really starting to drive the upward motion of the magma. And at some point up here, right before it erupts, it's more gas and less magma, and the magma is in small kind of clumps here, right? And then that's what actually erupts. That's the visible fountain that you're seeing when you see lava shooting out of the top of a volcano. So down here, bubbles surrounded by magma. Up here, magma surrounded by gas. And that gas pressure, once it finally reaches up here, that's what causes the eruption. And this is kind of a Hawaiian style eruption. So what are some of the precursors? We're going to do an activity in lab monitoring active volcanoes. And we'll talk a little bit about precursors, but I'll give you an overview here. The first thing to look out for with a potential volcanic eruption is a change in seismicity or earthquakes. So an increase in the frequency and the size of an earthquake near a volcano could be an indication that magma is moving up through the central vent and entering into the base of the mountain. And so that magma and that gas is going to start to cause rocks to shift and faults to open up and things like that. So you get earthquakes. And the type of earthquakes may change over long periods. And eventually you'll get, and this is a seismograph here, of some of those changes, right? And we see some kind of like, almost like P waves and S waves, right? But they're really close together. So, you know, this is indicative of you can tell when the earthquake is actually happening right there in the volcano. If you're at a monitoring station a couple miles away, you'd have almost, I mean, very little time between the P and the S wave. You'd know it's coming from the volcano. And they would be higher in amplitude. And then volcanic tremors start to begin. And once that happens, you're pretty much off to the races. Then we also get a change in shape. So deformation can begin to happen. That was like that bulge I was showing you. Here's kind of a side cross section of something like Mount St. Helens here. And, you know, you've got a magma intrusion here. They're calling it a cryptodome. I don't expect you to know that, but I never call it that. But anyway, you get a dome at the summit, and then you'll get bulging on the side, and that's sort of and then this red line here is kind of the pre-collapse. So the bulge starts to move its way up, and then you get a landslide eventually from the pressure of that bulge. And then once that slides, that gives the magma a place to expose the vent and erupt. And over here, you'll see that we also get the summit magma reservoir. This is almost like the volcanic neck that I talked about in the last lecture. And here's the deep magma system. If this all cooled, it would become a batholith, remember? But it's liquid now. And you'll start to get these shallow dikes moving up, and that causes deformation on the surface too, and earthquakes. You can get a change in the gas geochemistry. So that change includes the volume of gas being emitted and the type of gas. So you might be getting some sulfur dioxide, or maybe some oxygen being released in the form of like water vapor. But once you start to see a lot of CO2, that tends to be a red flag that your volcano is probably about to erupt. And then you can get changes in the hydrology. So if it's a snow-capped volcano, oftentimes you'll start to see melt in that snow. If you take the temperature of surface water bodies like lakes, sometimes rivers, oftentimes you'll see a rise in temperature of those bodies. And then just a loss of surface water bodies too, so more evaporation, which kind of goes hand in hand with increasing temperatures. The lakes will just start to get smaller and shrink down. So when it comes to eruptions, we sort of break that up into two broad categories, explosive eruptions and effusive eruptions. And the difference between those two is the amount of explosivity, right? It's an explosive volcano. It has a lot of gas under pressure in the magma. And so when it erupts on the surface, it suddenly releases all that heat and all that gas and all those kind of little chunks of magma that the gas bubbles are surrounding in the neck. And that's going to explode, very violently, right? That's a Mount St. Helens type eruption. And then you have effusive volcanism, which is more like what we see in Hawaii and Iceland. These are mafic lavas, and they tend to be less viscous. And so they don't explode as much as they just come out real fast and stay liquid for a long time. So those are like volcanic rivers, volcanic lakes, flood basalts, things like that. And explosivity of a volcano varies with the eruption interval. So how long since it last erupted, because it needs to build up gas pressure. So if it erupted recently, subsequent volcanic eruptions might not have as much gas in the magma because it was all expelled last time. So the subsequent eruptions might not be as violent. The the viscosity of the magma, and that's influenced by temperature. Obviously, if something's colder, it's more viscous than when it's hot. That is, it moves slower when it's cooler. None of it's actually cold, but cold in magma terms, so like 500, 600 centigrade. The composition of the magma, and this is mostly, and I want you to write this down or tattoo it on your arm or whatever, because this is important. The composition is mostly driven by the amount of silica in the magma, and then pressure. And that pressure is how deep is the magma, how much overburden on the volcano is there, and then the internal pressure of the magma too. How much gas is in there, and how much of that gas is increasing the pressure in the magma chamber or in the vent. And then that's closely related to gas content. So as you increase gas content, you increase pressure, outward pressure, not the pressure holding the magma down, like the pressure of the crust, but rather the pressure in the magma chamber pushing out on the walls of the magma chamber. That's going to cause more explosivity once it reaches the surface as well. So for eruption intervals, that's the longer the eruption interval, the higher the probability of a large violent eruption, which I already mentioned. And then gases too. So think about this. When you have a can of Coke or a can of whatever soda, it's got carbon dioxide dissolved into it. That's why we say it's carbonated. But it's sealed under pressure, right? And so that carbonation is in the solution, in the pop, but it's under pressure, so it's not forming bubbles yet, okay? It's just sitting in there under pressure. When you squeeze a closed pop can, a sealed pop can, you can feel that pressure. Then, when you open it, what happens? Well, if it's shaken up, right, and has even more pressure in it, that pop can explode and spray pop everywhere. Well, the same thing is true in volcanic systems. You've got dissolved gases held by pressure in the magma chamber, and as they move up, those bubbles start to form more and more and more, increasing the pressure. And then eventually, once it erupts on the surface, that's sort of like opening the pop can, right? You've suddenly relieved the pressure, and boom, all that gas just comes out of solution immediately. And it blows all kinds of hot rock and hot gases up out of the volcanic vent. And we get a lot of ash in these types of volcanoes, as opposed to volcanoes like in Hawaii and Iceland and in the East African Rift, which are more mafic and effusive, and they don't produce as much ash, and they're not generally as explosive. And I'll talk about why that is. So with viscosity, so resistance to flow, if you have a real thick felsic magma, so lots of silica, right? If it cooled underground, it would be a pluton and it would be a granite. But when it erupts on the surface, it's kind of a rhyolite or an andesite, so more felsic to intermediate. Those are going to be really explosive, whereas mafic lavas tend not to be, and they have less silica, and that's important. So why is that important? Well, more viscous has a difficulty to flow, like I said, and it also traps more gas. So more gas is allowed to build up in a more felsic magma or intermediate magma than it does in a mafic magma. And the reason is a mafic magma being thinner and hotter, the gas can move through that much easier, and it can get released in a more steady way. So there's no gas buildup per se. There's still gases in there, but when they erupt on the surface, there's just less gas content in the magma and therefore in the lava. So that gas just kind of diffuses out slowly. Whereas with like I said, the felsic magmas especially, more gas is building up underground in that magma before it explodes. And again, my spaghetti sauce water analogy that I did in the last lecture is a good way to think about this. Imagine you're boiling water, and then imagine you're boiling spaghetti sauce, right? What splatters on the counters and on your shirt and on the floor more? Water or spaghetti sauce? Well, it's spaghetti sauce. And that's because it's filling those, you get those nice big bubbles in a spaghetti sauce. And then when they pop, you just get more material being thrown around. So the relationship between viscosity and gas content, as I've mentioned, with silica-rich or felsic magmas, they're more viscous, like I said, and therefore they're able to trap gas a little bit better before the eruption. And so that combination of high gas content and high silica content make felsic eruptions much more explosive, potentially explosive. And here's a table down here from the textbook. If you have a basaltic magma, that is, it's mafic, it's got lots of magnesium, iron, things like that, a little less silica content, about 50% or less. That's the least viscous, so the most it makes it easier to flow and doesn't hold as much gas in. It usually has about 1 to 2% of gas content in it. So it doesn't form pyroclasts, which are, the ejecta, the material that's being ejected from the volcano in the form of hot rocks and bits of magma, things like that, lava. And when that erupts, the types of volcanoes it tends to form are shield volcanoes like Hawaii, basalt plateaus, which if you've ever seen a picture of Devil's Tower out in, I think it's in Wyoming, that's the remnants of a basalt plateau where a lot of it's been eroded away, but there's still remnants of it. And then cinder cones, which we see a lot in Iceland. Iceland sits, again, remember, Iceland sits on a divergent plate boundary, but it's exposed at the surface, similar to the East African Rift in Eastern Africa. Because it's at a divergent boundary, it's mostly erupting mafic magmas. And when that happens on the continent, or not on the continent, but on the surface, right, of like Iceland, it produces these small little cinder cones, which can still have a lot of lava coming out of them, but they're not explosive per se. Intermediate is usually about 60% silica content. It has an intermediate viscosity, about 3 to 4% gas content. And when that explodes, we get what we call a composite cone. And then rhyolitic magmas, which are felsic, are usually 70% or more silica. They have the highest viscosity, so resistance to flow. And so they trap about 4 to 6% gas, content. They have the highest tendency to form pyroclasts, so ash, bombs, explosive ejecta, and those form volcanic domes and pyroclastic flows. And I'll show you what each one of these volcanoes looks like in a moment. So as far as that ejecta goes, we kind of lump everything in together. Everything that erupts from a volcano we just call volcanic products. So what's in that? Well, for one, obviously magma, that's the liquid molten part, and that's at the base. And that magma is a mixture of solids, so some things that have begun to crystallize out of the magma, like olivines, pyroxenes, and things like that, plus gas in the form of bubbles or vesicles. So you have liquid and solid and gas all in the magma product. So for volcanic products, you have magma exposed at the surface, we call lava. You have pyroclasts, and that's anything that's ejected out of the volcano. And when they're large, we call them bombs, and they can be, the size of a baseball to the size of a car. And it can be fine particulates too, like ash. And that ash is rock ash. Okay, it's not like burning wood. It's It's literally exploded, pulverized kind of rock. And then gases made of the varying proportions of stuff I mentioned up here. And usually it's carbon dioxide, sulfur dioxide, etc. So pyroclasts, the more powerful the eruption, the smaller the pyroclast. Now that might sound weird, but I just imagine when that stuff explodes at the top of a volcano, if it's got a lot of power behind it, it's going to break up all that mantle product, or magma rather, and rock. It's going to explode that stuff with a lot more force. And so it breaks it apart. So the most powerful eruptions are like this one over here on the left. I mean, it's almost all ash. All that rock has been pulverized, right? This is what that looks like right before it cools. So here it's happening so fast that you can't even see that molten product there. But you do get ejecta of molten, lavas there. And, this is what down here, this is what that ash would look like when it settles on the ground. But you can see here that there was another eruption after this ash layer was laid down here, where this big bomb, about half the size of this woman here, landed in this spot, right? So these would be more powerful eruptions here, and then this was a less powerful eruption producing that because it didn't blow this rock apart. Even though, now it does produce some bigger ejecta, right? Even though it's less powerful. And typically when we think about lavas, they're much more common in more mafic eruptions, because as we saw in the felsic eruptions, they're more powerful. It tends to just blow all this material up, and it cools very quickly into ash or bombs. Whereas mafic lavas are much hotter. They're not explosive. So that's literally like turning on a faucet of lava coming out of the earth. And we have two different types. They're both named after where they've been studied primarily in Hawaii. So they have Hawaiian names. These are the traditional Hawaiian people's names for the different types of lava that erupt on the surface of the Big Island. One is Pahoahoa, and the other one is A'a. So pretty cool names. And then the gases that are common. So we have water vapor, right? H2O in the form of water vapor, gas. Carbon dioxide, those are the two most common. But you also get sulfur dioxide and hydrogen sulfide and some fluorine gases that also can be produced. And again, those are produced just by the pressure being relieved as the magma is moving up through the crust. And so once it hits the surface, that gas is free to go. There's no more pressure, just atmospheric pressure. And so that gas gets released. This is a picture of Tari Maddox, our department head and full-time geology faculty member back in the day when she worked for the Hawaiian Volcano Observatory. So this is a picture of her from National Geographic, 1992, taking some measurements here at the Kilauea Observatory. And here's a picture of a composite volcano releasing tons of gas in the form of sulfur dioxide and hydrogen sulfide. I encourage you to look at these links. These are different volcanic eruptions. They're pretty cool to give you a sense of what these volcanoes look like when they're erupting. So where do we find volcanoes? Well, really, we find volcanoes anywhere where there's magma close to the surface. And as we've talked about, the different tectonic settings where that happens, obviously divergent plate margins. So you see we have a volcano here at on Iceland. There's active volcanoes along this mid-continent rift as well, or oceanic rift, divergent boundary here, down in the South Sandwich Islands. We have volcanoes all along the coast where there's subduction, and here you'll remember that the Pacific Plate is subducting underneath the North American and South American continents. We have, and those are part of the much larger ring of fire, right? So this plate here is subducting underneath a couple microplates over here and also under the Eurasian plate. It's subducting under the North American plate up here at Alaska. With that, remember that's an oceanic to oceanic convergence, and again subducting here, and then we can get intraplate volcanoes as well, and that's like the hotspot in Hawaii. There's hotspots over here in Europe. There's also subduction over here in Europe as well. That's like Vesuvius, Mount Etna, and so on. So those are the three. We don't see volcanism conspicuously at transform boundaries, right? Because those are plates that are moving side to side. They're just sliding past each other. There's no magma bodies there. So here's a little bit more in depth. So this is a divergent boundary here. I had this slide in the previous lecture. Here you've got, remember, partial melting, relief of pressure. It forms a magma chamber here. And then, that magma chamber is releasing products up into the void space being created by the two plates that are moving apart. And those tend to be in the oceans, but you do have them on land, again, like I said, in Africa and in Iceland. Subduction, again, here we've got volatiles reaching just the perfect depth to kind of flux melt this mantle product here that moves up through the oceanic base and then up through the continental crust, and that can either cool and form a pluton or erupt on the surface as a continental volcanic arc. And then here we have that hot spot. So this is just a mantle plume that's heating up the moho here, the boundary between the mantle and the lithosphere. Then it moves up through the lithosphere and erupts on the surface as a volcanic island that eventually will erupt enough material to pop up out of the ocean. So volcanism can occur either along submarine continental rifts, like I said, in the ocean, or on continental rifts, like in the East African Rift. And these are most closely associated with the mantle rock, right? So mantle, probably because oceanic crust is thinner and it sits lower. There's just a lot more magma recently sourced from the mantle that reaches up to the rift, because that's where the crust is the thinnest on the planet, right? And so these tend to be mafic. That's why most of our oceanic crust is made out of basalt. And at convergent boundaries, you have mantle and oceanic or continental crust, so you can get a mixture of mafic and felsic magmas. Intermediate is most common, some mix between the two, because those felsic magmas and those mafic magmas are mixing together. And for continental to oceanic convergence, remember, as this plate is subducting down and activating this stuff down here through flux melting, as that stuff's moving up through this continental crust, it's melting a lot of that host rock, and it's introducing more silica. So by the time it erupts, it's not really a mafic magma anymore. It's more like an intermediate magma that's got some amount of silica in it. And the same is true of oceanic to oceanic convergence too. Maybe not as much silica here as you have up here, because it's not moving through as much continental crust, but it is moving through some amount, right? So it's still picking up silica as it goes, just maybe not as much. And this tends to be where you get the explosive magmas, or explosive volcanoes, due to gas content and silica content. And then intraplate, again, we've got, they tend to be mafic on the oceanic crust and felsic to mafic on continental crust. So Hawaii has mafic, and then a place like Yellowstone, were it to erupt, because it's over a hot spot too, that would be more felsic and mafic, so more intermediate. And here's just the process of what would happen. So you've got your mantle plume rising up through the mantle. It hits this area here. And what you're seeing here is not this magma, this hotspot moving past this boundary. This hotspot pools at the bottom of the lithosphere and then begins to melt that lithosphere. So that's going to have a little bit different composition than the mafic magmas down here. But you still get it rising up through fairly thin oceanic crust, and so these lavas tend to be more mafic. And on the continent, you can get these giant flows because it stays hot longer on the continent. In the ocean, obviously, it cools down much quicker. And so what we tend to see there, like in the case of Yellowstone, you get these huge basalt flows, and we call those flood basalts. And if you've ever been out to the Snake River Plain or the Columbia Gorge out in Washington, the Columbia River, it's cutting through just hundreds of feet of basalt that pooled up. And this is also how you can get things like lava lakes and things like that. And you get crustal melting, right? And a caldera when it's on the continent as well. So that stuff will erupt. Sometimes it has some explosivity if it's moved through some continental crust. And so what's left is a crater, basically, that's been blown out. And we call that a caldera. So types of volcanoes, we have shield volcanoes, like I said, like Hawaii, stratovolcanoes or composite cones, calderas, fissures, cinder cones, and lava domes. And some can be put together, but tend to be dominant in a particular tectonic setting. So a shield volcano, again, like Hawaii, it's mostly made of, it's formed by more fluid basaltic lavas. And it tends to, like, these are erupting and then running down due to gravity, running down into the ocean. And so that's what these whole islands are made out of. And we call them a shield volcano because they're kind of shaped like a shield here, right? They tend to have low slopes. They tend to be in the middle of plates, oceanic or continental. And they tend to not be as tall on the surface, although I do want to point out the largest mountain or volcano from the base to the top isn't Mount Everest. That's just the highest above sea level. The tallest actual volcano or mountain on the planet is actually Hawaii's Big Island. But most of it's underwater, so we don't think about it like that. Here's an erupting portion of a shield volcano, and this is on the continent, and you can see that it just has this kind of low slope, sort of rounded. Then we have stratovolcanoes. These are steep. These are made of successive layers of lava, usually rhyolitic or intermediate lavas, and then the pyroclastics that get thrown up and ejected out during the explosion that fall to the slopes here and run down. They tend to form, a lot of the volcanoes we see on the West Coast, like Mount St. Helens, Mount Hood, Mount Shasta in California, places like that. They're generally felsic to intermediate in composition, and like I said, they form generally at convergent plate margins. So this is that stuff that is coming from a subduction zone and moving up through a bunch of continental crust before it erupts. And it has a crater or a vent. Sometimes it can have little side offshoots that form these little, what we call parasitic cones. So not the main vent, but sort of on the sides of the mountain. All this pyroclastic material was ejecta that's since settled around the vent. You can have active lava flows, either on the surface or recorded in the layers. And this is all being fed by a single conduit, which we call a central vent or a neck. Here's a perfect example of a stratovolcano. These are just kind of textbook mountains that we think of, but these aren't formed from, the same way the Himalayas are, right, where it's continent to continent convergence, and it's just pushing basement rock up. This is from erupting, is how this is formed. And these are the real explosive ones, and for some reason we love to build cities right by them. So anyway. Then you have cinder cones, which is very similar to a stratovolcano, but just much smaller. The central vent is filled with more rock fragments, so you can still get lots of pyroclastic material, but these tend to be mafic, so they're not as explosive. So these are mostly formed by just flowing lavas, and a little bit of gas content being trapped in the mafics gives you just a little bit of this kind of fine-grained stuff when it comes out. There's a cinder cone there in Iceland erupting. So you can see it's coming out with some force, and that stuff's cooling in the air, and then when it falls, it just becomes these pyroclastic materials. But there's not as much gas content. There's still pressure being relieved, so it's still shooting out. There's not as much gas content, so it's not as explosive, so we're not getting a lot of ash as much as we're just getting lava cooling in the air as it's falling. So here's a kind of a size comparison, relative size comparison. So here's a large shield volcano like the Hawaiian Islands. And here's what a composite volcano or stratovolcano would look like compared to that. So steeper, has a central vent exposed at the top. Then we can get smaller shield volcanoes. We can get volcanic domes, and then we can get cinder cones or scoria cones, and those are the smallest. And then remember we talked about Olympus Mons on Mars. It is a large shield volcano as well, and it would be way too big to even put on this slide. I was telling some students the other day, it's Olympus Mons is so big, when you're standing at the base of it, you cannot see the top of it. It's many, 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 many kilometers tall and long. Then we can get calderas. So basically you have a stratovolcano here that's erupting material. As it's erupting that material, this magma chamber here is releasing its material, okay? So once that happens, you get a space in here where there's no material, right? It's all been erupted out. And so that whole thing can collapse. And when it collapses, it forms something similar to this. And then in that void space on the surface that collapsed down into the magma chamber, oftentimes you'll get a caldera. And there's a famous one in Oregon called Crater Lake. And this is a national park. People go swimming there and go boating there. It's got a little island in the center where after the collapse, another bit of magma began to make its way up from the chamber, forming a new conduit, and then it started to erupt another volcano inside the caldera, and this is very common. And I think that volcano is still active. I don't think it's erupted in the last couple centuries. I might be wrong about that, but now this whole thing is filled in with water, and you've got just this little volcano sticking out in the middle of the lake. And here is a picture of it. So this was a big, huge explosion, kind of explosive eruption. And then all that stuff collapsed down into the magma chamber. And then here's that little island here, stuck in the middle, called Wizard Island. And this is the parking lot. You can go to kind of observe that. And then you can rent boats and you can go out on this thing in the summertime. Then we have fissures. These tend to be when you have we were talking about dikes in the last PowerPoint presentation. So imagine if a dike made it all the way up to the surface and started erupting before it cooled underground. We get something called fissures. And here you get a lot of lava fountains and then basaltic flows away from the fissure. And a fissure is a long crack in the crust, and it erupts those basaltic fountains. And these are most common at divergent plate boundaries, where you have normal faulting and you have some kind of a rift, and that rift is exploding or erupting lava up onto the surface. We see these in the East African rift and in Iceland especially too. So here's a fissure in Iceland, I believe. So here's the long faulted crack here. Magma is making its way up and erupting on the surface as lava. And then here's the basalt kind of flowing away from it. So lava domes, these tend to be made entirely of viscous lava, right? So felsic to intermediate. And they can be there on their own, or they can be capping a stratovolcano. So you can think of that island in Crater Lake being similar to this, but here you've got a caldera, and then you've got a lava dome forming in the middle of it, and that's just from lava pushing up and and creating a bulge here, right? And there might be some eruption on that dome somewhere, but mostly it's just material from the caldera being pushed up like a bubble. So here's a good, illustration of where we find different types of volcanoes. So for volcanic island arcs and things like that, we get those at oceanic to oceanic subduction. Shield volcanoes we see at intraplate, so hotspot volcanism from decompression melting. Composite volcanoes and stratovolcanoes we tend to see at oceanic to continental subduction, and that's because that stuff needs to move through the continent to pick up enough silica that it's explosive enough to be a stratovolcano. We can get rift valleys with flood basalts like in Africa, and that's decompression melting at a divergent boundary, but a divergent boundary that's that's on the continent, which is a little different than up here, where at the mid-Atlantic ridge or the mid-oceanic ridge is out there, we're getting the same basic plate motion, but one is under the ocean and one is on the surface. So here that basalt can't flood, right? It just cools immediately and forms new oceanic crust. But here that rift is opening up, and this stuff stays liquid for much longer, and so you get a rift valley that has lots of flood basalts forming in it. And you can get flood basalts at intraplate as well, like the Deccan traps in India. So we'll finish up here with a dozen or so slides on volcanic hazards. And remember, hazards tend to only involve situations where there is stuff to be destroyed or people to be hurt. So unless you're a bird or a squirrel or a river, volcanic eruptions are hurting you. But when we think of them as a, kind of harming society, harming humankind, it's because we choose to populate ourselves around active volcanoes. So let's talk about some of those hazards. A quick overview, and then I'll dive into each one. We have lava flows, ash falls, pyroclastic flows, and that's a mixture of pyroclasts and gas. We have lahars or mud flows. This is when you get pyroclastic material, hot gases, and superheated external water rushing down the side of a volcano. You can think of this like a boiling hot mud flow. Really nasty. You can just get some gases released that can be hazardous. You can have the effect on weather and climate that those gases produce. Obviously, you can get tsunamis if you have a large enough volcanic eruption under the ocean, and the earthquakes associated with said eruption, and then giant volcanic landslides. So lava flows are just molten rock moving across the surface. Definitely check out all the links that I've put on this when you go into the actual lecture slides themselves. Definitely click on these and you'll get a sense of all of this. There's some really crazy, dangerous videos that people took. So molten rock moving across the ground surface, that's a lava flow. Obviously, you don't want to get caught up in that. This is literally molten rock. It'll melt your clothes off, and then it'll melt your legs off, and then you just become part of the lava flow. Then also, I want to talk about the impact, that is the proximity of damage to the eruption and the types of damage. So for lava flows, the impact of these is close to the volcano, right? The lavas tend to cool down once you get far enough away, so they're not as dangerous. But I mean, you got to think, the ones in Hawaii, some of those mafic flows, they go on for, 10, 20, even 100 miles sometimes. Kind of depends on how hot the magma is and how much material is being pushed out. And the damage you tend to get is these flows will bury things and they'll catch things on fire. Then you have fine fragments of ash raining out of a big eruption plume. And when that settles, we call that ash fall. And that stuff can fall all over, structures, cities, towns, forests, anything like that. And it can choke out vegetation. It can gum up machinery, engines, things like that, by suffocating them, or in the case of planes like that Iceland eruption back in 2010. As planes were flying close enough to this, the one in Iceland, some of this ash gets in their engines and it superheats, and then it cools into bigger materials, and that stuff can go into the engine and mess the engine up. The impact of ash falls is close to far away. These plumes choke out forests and can damage structures, cover things up around the volcano. But then that plume, if it gets high enough up into the jet stream, then it can travel all over the place. It can travel across the whole planet, essentially. So when it's close, we call that proximal. So the proximal damage would be death, the collapse of structures, and obviously darkness as it blots out the sun. The distal, or far away or distant impacts, are air travel, crops, because they can block out the sun and cause crops to fail. It can damage cars by choking out the engines. And it's not good to breathe this stuff either. So, we just kind of had that with the forest fires up in Canada. Imagine that, but the ash is actually a mixture of magnesium and iron and uranium and all kinds of stuff that you would get. So not good. And you get pyroclastic flows. This is a turbulent flow of hot gas and ash. So not so much water, but much more just hot gas and ash. And you can get proximal damage to intermediate distances, and that's death and destruction just across the board. This is, after lahars, this is definitely the most destructive. I urge you to watch this video. This stuff can move at hundreds of miles an hour, and it's just sort of cascading down the sides. You cannot outrun it. If it swallows your car, it can heat everything up to hundreds of degrees in an instant. So it'll burn structures, it'll suffocate you, it'll choke out forests. It's nasty. Then you have lahars, which is basically like a pyroclastic flow, but with a lot of water in it and mud. And these are hot, like a pyroclastic flow, but they're liquid now too. And they have similar ranges of damage. They cause death and destruction, and they are the most hazardous. They stay warm longer, so they stay hot longer. They move faster, and yeah, they're nasty. And then gases that can be produced are superheated water vapor, CO2, sulfur dioxide, and hydrogen sulfide. And what this can do is it can kill plants and animals nearby, right? And far away, it can aggravate lung and respiratory disorders, and it can cause changes in climate and weather. So when you release ash and gases into the atmosphere, basically that limits the amount of heat and light that enters into the atmosphere, and you can get a cooling of the planet. So there have been glacial periods that are very much driven by lots of volcanic periods just before. So volcanoes definitely have a huge impact on climate over time. As they're releasing more and more oxygen or hydrogen or anything into the atmosphere, they can cause the overall climate to cool down or the overall climate to heat up. causing either kind of snowball planets or glacial periods, and then runaway greenhouse. This is probably what happened to Venus, by the way. Probably just had so much volcanic activity at one time, it released so much hydrogen sulfide into the atmosphere, you get a runaway greenhouse effect. And now, you know, the surface of Venus is hundreds and hundreds of degrees. And then you can get giant volcanic landslides. This is called sector collapse. This is when whole sectors of the volcano fail and cause kind of an avalanche, a rock avalanche, right? And this can be damaged close by or far away. This is what killed that geologist in Mount St. Helens back in 1980. And the damage here is just complete devastation, right? Forests completely wiped out, waterways completely choked up. Any structures would just be covered in the avalanche debris, and super bad news. Definitely click on all the links. Particularly, there's one. It's pretty sad, but it's powerful to watch. There were these two volcanologists. I think they were French. It's a husband and wife who did a lot of work together over decades and decades and decades. And they got a little too close to one, and they were actually killed by a pyroclastic flow. And there's footage of it erupting and them running away down the street, and it eventually overtakes them, and the camera shuts off. Pretty crazy stuff. So click on all the links, check that stuff out. I went fast through this one because I wanted to get it up, but you know, watch it twice if you missed anything or you need to go back and review anything. And we'll do a little bit of a volcanic activity in the next lab that I've posted on Blackboard, and we might do another small activity on Tuesday of next week. Not sure yet. But anyway, so this concludes volcanoes. I finally feel a little bit caught up, so that's awesome. Hopefully I'll get these to you at the beginning of the week going forward. Have a great day. Be sure to watch Igneous too if you haven't already, and see you guys soon.